Here we see some sodium metal that has just freshly been cut because it's got the shiny luster of metal out in the open. Oxygen's going to attack it and turn it all white in no time. Extremely reactive. So this was made by man-made somehow. And here's chlorine gas, yellow gas with a pungent odor. Highly reactive and poisonous. This was the first known chemical warfare agent. I'd rather take a bullet to the head or to the heart versus dying a painful, slow, could be quick. I mean, an hour, 15 minutes of suffering. All right, so point of these two deadly poisonous elements. And this morning, I ate grits with canned peaches that I bought from Palisade, Colorado. And those grits would have been really disgusting. All hot cereal's disgusting if you forget the salt. You like your hot cereal without any salt, evidently. All right, so the interesting thing is those two deadly elements put together make a compound, sodium chloride. Real common, you can buy it in boatloads at the store. It's on everybody's table. The point here is the properties of a compound are much different than the properties of the element. Those two elements, wouldn't want to take any one of them into my body. Like taking a little piece of sodium in your mouth, it'd release a lot of heat. It would turn extremely basic, so you'd have base burns, thermal burns, but together in a compound, totally different properties. And how many of you ever looked at a little crystal of sodium chloride? What shape is it? Yeah, it's perfect little cube. And here's why we might see why. So the sodiums are positively charged. Sodium gave up that one valence electron notice it's right there in that column. Let me shoot my phone and see what it does to the video. And chlorine, right next to argon, so it gains an electron, and it's this electrostatic force holds this ionic substance together. We're going to see shortly what makes something an ionic compound, what makes something a molecular compound. So I wanted a mixture. Now, of course, there's probably pure hydrogen in this dirigible, and there's oxygen outside. So when they first started making dirigibles, they used hydrogen. You can see hydrogen, oxygen. Hydrogen's very flammable, and you form this compound. We almost have a chemical formula here. It's not balanced. Notice there's only one oxygen depicted here. But we can just talk about the air here. You know, if you train for a marathon in LA, then you come up here, you get more winded because there's less oxygen. So mixtures have variable composition. So possibly, if we think about this as a chemical equation, we actually have a leftover oxygen atom. Here's my two hydrogens. There's my two hydrogens. I have two oxygens. Here is only being depicted one. So here, water, when we have H2O, the relative amount of hydrogen and oxygen we say is fixed. We say water has constant composition, fixed proportions. So down here, that's how we differentiate a mixture from a compound. Mixtures have variable composition. Compounds have fixed composition. And a compound is a pure substance. Last chapter, we learned that elements and compounds are pure substance. Joseph Proust formally stated this idea that elements combined in fixed proportions to form compounds. And we call it the law of constant composition. All samples of a given compound have the same proportion of their constant elements, also known as the law of definite proportions or law of constant proportions. I suppose I could mangle it and say constant composition. Everybody's clear on that idea. Compound has constant composition or proportions. So here's some water. If we took 18 grams of water and decomposed it, we would always get 16 grams of oxygen and 2 grams of hydrogen. And if we ratio the smaller one to the larger one, we say that hydrogen and oxygen come together in an 8-to-1 ratio by mass. Here's ammonia. I should have fixed up my slide. Ammonia, NH3. But Joseph Proust, they didn't have any formulas. They hardly knew anything. Well, they could go make their wanes, and they found these ratios. So here, decomposing 17 grams of ammonia will produce 14 grams of nitrogen and 3 grams hydrogen. So no matter where you find the nitrogen or the ammonia, if it's ammonia, you're always going to get this 4.7 to 1 ratio. H2O2, anybody ever see that before? Comes in a little brown bottle at the grocery store. Hydrogen peroxide. Now this always comes out kind of like this. Oh, Eric, you didn't need your calculator. I start talking and my brain shuts off. Should have did that in my head. Hydrogen peroxide is always going to have this ratio. Water is always going to have that ratio. That's how we recognize that we have a compound. Compounds have constant composition with respect to mass because they are composed of atoms in fixed ratios. And our subscripts tell us that, 2 to 1. If it's not 2 to 1, it's a 1 to 1. Chemical formula indicates the elements present in a compound and their relative number of atoms of each. So there's our H2O. Tells us that hydrogen atoms and oxygen atoms combined in this ratio. The formula contains the symbol for each element accompanied by a subscript indicating the number of atoms of that element. Now notice we don't have a 1 here, but it's understood. By convention, a subscript of 1 we omit. So we have some conventions. There might be a few exceptions. Chemical formulas list the most metallic element first. So table salt, sodium chloride, we always list it NaCl. And when I look at this, I have a hard time even saying it. Chloride, sodium, chlorine, sodide, it just seems real awkward. So the most metallic. And since we have this diagonal stair-stepping line there, with the metals over here and non-metals over there, we can come up with a trend line that looks like this and say metallic character increases. So francesium is the most metallic element. Helium is the least metallic element. And that will get us to write carbon dioxide as CO2 and not O2C. All right, among nonmetals, those to the left in the periodic table are more metallic-like. Got my trend arrows right? And are normally listed first. So like NO2, NO, not like this or that. Within a single column in the periodic table, elements towards the bottom are more metallic-like than elements towards the top. Any questions about the periodic trend of metallic character? Can help us in our naming. Elements on the left are generally listed before elements on the right. The specific order for listing non-metal elements in chemical formula is shown here in this table. There are some historical exceptions, which the most metallic element is named first, such as the hydroxide ion. And it's an easy exception to deal with because there's these things called polyatomic ions, and you just memorize them, and you don't have to figure them out from a trend or a little law. Some chemical formulas contain groups of atoms that act as a unit. That's these polyatomic ions. When several groups of the same kind are present, their formula is set off in parentheses with a subscript to indicate the number of that group. Many of these groups of atoms have a charge associated with them, and they're called polyatomic ions. We just looked at hydroxide. Let me just think about this a little bit. How about if I combined magnesium and hydroxide to get magnesium hydroxide? I'm going to have to do something like this. I get 2 of these, and then we have enough negative charge to neutralize all that positive charge. And this illustrates this idea of parentheses and that subscript. To determine the total number of each type of atom in a compound containing within a group, within a parentheses, multiply the subscript out as outside the parentheses by the subscript for each atom inside the parentheses. Now let me do one of those. Let's say we have magnesium nitrate. We'll see nitrate in a little bit. It's NO3 with -1 charge, so I'm going to need 2 of those. So how many oxygen atoms are present? How many oxygen atoms? 6, right, because here is nitrate, NO3, and I have 2 of those. And so yeah, we go 2 times 3 and get to 6. Should have done something different. How many of you want to see me do something different? And the hardest one I could come up with. All right, calcium phosphate. What is the formula for calcium phosphate? Well, what's the least common multiple between 2 and 3? I warmed you up Monday. 6. 2 goes into 6 how many times? All right, now I got to put my phosphate in parentheses. And 3 goes into 6 how many times? All right, so now I could say how many oxygen atoms are present here? Right. And how many phosphorus atoms? Yep. Empirical. What does empirical mean? It means experimental. An empirical formula gives the relative number of atoms of each element in a compound. Sometimes it's different than a molecular formula. Molecular formula gives the actual number of atoms of each element in a molecule of that compound. For example, the molecular formula for hydrogen peroxide, got you all warmed up with that, H2O2. Well, when you go into the lab, you find that these combine in a 1-to-1 ratio, and you come up with something that looks like this here, a 1 and a 1. So I always say the molecular is a multiple of the empirical. For H2O, it's a multiple of 1. The empirical and the molecular are the same. The molecular formula is always a whole number multiple of the empirical. For many compounds like H2O, the molecular formula is the same as the empirical formula. We'll look at that more later. A structural formula can use lines to represent chemical bonds and shows the atoms in a molecule connected to each other. We can see a little more shape going on with that. And we have molecular models. Typically, we have this color scheme, not always. Carbon being black's very universal. Most of these, that old model kit we have, hydrogen's off, it's colored. Molecular models, 3-dimensional representation of molecules. We can use those to represent compounds. We use 2 types of molecular models, ball and stick and space filling. Ball and stick, pretty self-explanatory, just connected together, color-coded. Space filling, the atoms fill the space between each other to more closely represent our best idea for how a molecule might appear if we could draw it to scale. So here's just a molecular formula, CH4. Here's how we might draw it in paper with lines representing bonds. Ball and stick, we see that it's not flat like this drawing. It actually has a 3D shape, and from various experiments, we know that there's not this region of like empty space there, that there's electron clouds everywhere. So how do we classify matter? We did this a little bit in the previous chapters. Pure substances are either elements or compounds. We can have elements that are atomic and elements that are molecular. Molecular means we have a molecule. We have 2 atoms bonded together. So a good example here is like neon or argon. But if we go to a gas like oxygen or nitrogen, we find that those atoms are bonded together. So there's a bunch of what we'd call diatomic elements. Mostly the non-metal gases like to bond to themselves. O2, N2, H2. Now let's look at compounds. Our compounds come in 2 flavors, molecular and ionic. How do you tell which is which? Ionic, we always have a metal and a non-metal. Molecular, made from non-metals only. You kind of see that over here. Atomic elements are those that exist in nature with single atoms as their basic units. All of our metals also fall into the situation. Copper, zinc, iron, silver, platinum, gold. Molecular elements do not normally exist in nature with a single atom. You don't find a single atom of oxygen lying around anywhere on the surface of the Earth. Either bonded to itself or bonded to hydrogen in the form of water, or bonded to silicon to make like sand and a bunch of dirt-like compounds. So we call these diatomic molecules. Two atoms of that element bonded together, that represents their basic unit. Diatomic elements are diatomic molecules. All right, this is missing the caption. Diatomic elements kind of make this big 7. 1, 2, 3, 4, 5, 6, 7. Those are our diatomic elements. Now these here we call polyatomic elements. Like sulfur can exist in these other forms. In my Chem 1 lecture slides, I have a bunch of different types of phosphor. White phosphorus, red phosphorus. They're all phosphorus, but different amounts of phosphorus stuck together. So when we see a compound, we want to be able to tell whether it's molecular or ionic. And one reason why we want to do that, we name molecular compounds with one system and ionic compounds with another system. Not to be difficult, but because it makes sense, and that's how science has opted to do it. Molecular compounds are formed from 2 or more nonmetals. So I've told you this, and I'll tell it to you again until it's drilled into your brain and you never forget. The basic unit of molecular compounds are molecules composed of the constant atoms. Ionic compounds contain 1 or more cations paired with 1 or more anions, are usually formed from a metal and a non-metal. The basic unit of an ionic compounds are called formula units. When I go NaCl, that's the formula unit. But at the beginning of today's lecture, you saw that big square that had all those positive and negative spheres. And that was all ionically bonded together, and there was a cajillion atoms, but this is the simplest unit. So that's why we call it a formula unit. See, this sodium's attracted to all those chlorides, this chloride attracted to all those sodium cations. So this is the basic unit. And here's some salt somebody carried around in their pocket. Look how smooth it is. Most table salt's got a little sharper edges than that. Now here's some dry ice, and here's CO2, and the CO2 represents an actual molecule. So here's a molecular compound because carbon and oxygen are 2 nonmetals. This is an ionic substance because we see a metal and a nonmetal. So to review, the elements that form ions with a predictable, no, you need to review that. And so there's quite a few. I can say, what's the compound when fluoride combined with strontium?